So now we're going to look at the electronegativity difference between two atoms bonded to each other and how that's related to the bond type. All right. Now, firstly, let's deal with a situation where we have two identical atoms bonded to each other. If we have such a situation, then obviously both atoms will have the same electronegativity values, and therefore both atoms will share the bonding pairs equally. So in that situation, we say that the bond is a nonpolar covalent bond. All right. Now, if you have the same situation, but they're different atoms, then if the electronegativities differ significantly, then what that means is that the electron pairs will not be shared equally, right? And in that case, what you'll have is that the electrons will be drawn closer to the atoms that has a greater electronegativity. And therefore, this bond is said to be a polar covalent bond, all right? Now, you can have a situation where the electron negativity values are so different that instead of sharing the electrons unevenly, the electrons are completely transferred from one atom to the other. And usually this happens when you have a metal bonded to a nonmetal. In that case, the bond is said to be ionic. So therefore, the ionic bond is basically the most extreme case of a polar bond, but it won't be a covalent bond because the electrons are not being shared, because you have the complete transference of electrons from one atom to the other, right? So basically, these are the three types of bonds that we'll be dealing with based on the electronegativity difference. You have the nonpolar covalent bond, you have the polar covalent bond. In the case of the nonpolar, the electrons are shared equally. In the case of the in the case of the polar covalent bond, the electrons are shared unevenly, but they're shared still. And then you have, in the case of the ionic bonds, where the electrons are not shared at all, you have the complete transference of electrons from the least electronegative element, which is usually a metal, to a more electronegative element, which would be a nonmetal. All right? Okay, so what this is showing you is basically the range of possibilities in terms of the electronegativity difference and the type of bonds associated with those differences that exist between atoms, right? And there's no sharp cutoff point when you look at the difference between ionic and covalent bonds, or for that matter, when you look at polar and nonpolar bonds, all right? But there's some criteria that we use in some textbooks, right? So what I'm going to show you here are the different criteria that are used to determine whether or not a bond is polar covalent, nonpolar covalent, or ionic. All right, so let's talk about nonpolar covalent bonds. What's the criteria that we use to establish that a bond is nonpolar covalent? Well, for one, if you have a bond between two nonmetals, right, and there's an almost equal, if not equal, sharing of electrons. So what that means basically for this criteria, if the difference in electronegativity ranges from 0.0 to 0.4, then the bond is, for most purposes, considered to be nonpolar covalent. And some examples are shown here. Now, obviously, if you have two identical atoms, then the difference would be 0. So that would be nonpolar covalent. But like if you look in this case here where you have chlorine bonded to bromine, and you look at the difference in their electronegativity values, you see it's 0.2, then that falls within the range here. So therefore, we say that this bond would be, based on this criteria, this bond would be nonpolar covalent. Here's another example. The bond between the hydrogen and silicon atom, the difference is 0.3, which again lies within this range. So therefore, that bond is considered to be nonpolar covalent. All right? Then we get to a situation of polar covalent bonds. And in this case, you have an unequal sharing of electrons, and the difference in electronegativity that we use as a criteria for establishing a polar covalent bond is from 0.5 to 1.7, all right? So these are just some examples here: oxygen to chlorine, chlorine to carbon, oxygen to sulfur. In each of these cases, the difference in their electronegativity values is lies within that range. So therefore, these bonds are essentially polar covalent, all right? And then finally, in the case of an ionic bond, the criteria that we use to determine whether or not a bond is ionic is whether or not the electronegativity difference is 1.8 or greater. So this is typically between a metal and non-metal. So some examples are shown here. the chlorine to potassium bond, the sodium to nitrogen bond, the cesium to sulfur bond. All of these has an electronegativity difference values at least 1.8, and therefore all these bonds are considered to be ionic. All right, so basically that's how we determine whether or not a bond falls into any one of these three categories. So how we depict these bonds in terms of polarity? Well, what we're looking at here are diagrams that we use to show how the electron cloud distribution occurs in each of these situations. In the case of the hydrogen molecule and the hydrogen chloride molecule. In the case of the hydrogen molecule, the electrons would be evenly distributed between the two atoms because they're identical, right? However, in the case of the hydrogen chloride molecule, what you'll see is that most of the electron cloud will be, on average, closer to the chlorine compared to the hydrogen. And therefore, you have the displacement of the electron cloud towards the chlorine, and therefore, as a result, this bond is polar. Now, what will result is what we call a separation of charge, and we can represent that using this symbolism. Delta minus, which means a partial negative charge, right? And then you have delta plus, which is a partial positive charge. Partial positive. All right? So basically, that's why the bond is considered to be polar. And down here, we have what is called an electrostatic model, which shows you basically how the charge separation takes place. The red represents negative, the blue represents positive, and that shows you how the electron distribution is taking place in the case of hydrogen chloride, all right? So that's basically that. Okay. Another way of depicting the polarity of a bond is using this arrow with a cross at the tail. Basically, that tells you that the convention is that the arrow is pointing from the positive end to the negative end of the bond. So that's why the arrow is pointing towards the chlorine in this particular situation, right? So that's another way of representing the separation of charge within the bond, and therefore the bond is said to be polar, all right? Okay, now let's look at this example here. This question says, use the electronegativity values to determine the order of polarity of these bonds. So you'd have to go back to the table. Let me just remind you of what the table is. This table in order to answer that question, all right? Now, I have a copy of the table in front of me, so I'll be able to refer to it in order to answer the question. But the first thing I would notice in this series is that you have two identical chlorine atoms right here, right, bonded to each other. So obviously the difference here would be 0, right? So I'm just going to put 0. Hold on. Let me erase this here. Go back to this, and then let me use black ink here. Okay, so the difference here would be 0, all right, in the case of chlorine. Now, for bromine, I'm going to look up the value here on my copy of the, okay, what's going on here? Okay, so, okay, so in the case of bromine, the value is 2.8 here. In the case of chlorine, it is 3.0. So the difference here would be 0.2. In the case of chlorine, it is 3.0. In the case of fluorine, it is 4.0. So the difference here is 1.0. In the case of hydrogen, it is 2.1. In the case of chlorine, it is 3.0. So the difference here is 0.9. And finally, in the case of iodine, it is 2.5. In the case of chlorine, it is 3.0. So the difference here is 0.5. So these are the values we're looking at here in order to establish the order of polarity. So the answer would be that chlorine to chlorine would be the least polar because that's 0. And then the next in line would be bromine to chlorine, right? Because this is 0. This is 0.2. And then the next in line would be iodine to chlorine. because that value is 0.5. And then the next in line would be hydrogen to chlorine, because that is 0.9. And then the next in line would be chlorine to fluorine, and that is 1.0. So those are the answers. All right. Okay. So we're going to stop here. And let's see, the next topic we're going to discuss are certain molecules that don't follow the octet rule. All right. Okay. Until next time.